Okay, so Mike and I are continuing to work on the sort of the core intuitions. The thing that has been surprisingly difficult is the collection logic, getting the collection logic separated out and accounted for appropriately. So if you look at let me see if I can find a way to, yeah, here we go. I'll just do this. Get okay. Here we go. So I've got a few slides here. There we go. So let me make a copy of this one. Duplicate and all right. So I guess I'll just make a copy of this slide here. And we can start manipulating. So I think it's, it's easy to see if you have, a power set, how the power set of some set, how that corresponds to a Boolean algebra. And if you have a power, if you have a if you have different notions of power set, that'll give you different kinds of logic. So you can get an intuitionistic logic with a different notion of power set. And this is sort of the basis of or some of the insights that go along with Topos theory. And when you generate the when you generate the logic in the naive way for these simple structures like the monoid, what you want to do is to have the formulae that correspond to how you collect the witnesses to correspond to some notion of collection. But the thing is that the notion of collection is not really well understood. And it's not really well understood from a classical mathematical point of view, nor from a computer science programming point of view. And, as evidence for this, how many times has the Scala collection library been rewritten? Right, so there's at least 3 times this Scala collection library has been rewritten. If they could rely on a mathematical framework and say, okay, this is what collections are, then they wouldn't have had to rewrite that library so many times. And if you look at how it changed, it wasn't a straight line. Let's put it that way.
And now, if I can add, we have this sequence which is not completely clear how to use it, and is it least better? And
correct, and the further away you get from the functional languages, the worse the story gets. Like by the time you get to the language that underpins most of the statistical and statistical and financial statistical libraries, which is the language R, it's really, really ad hoc. It's really terrible. And so what we want is the logic to correspond to a notion of collection and a notion of collection to correspond to a notion of logic. The two ideas, so the aim is to get the two ideas to become coherent. The reason I focused on monad was because the monad has a really it's on the one hand simple, and on the other hand there's an interpretation of comprehension. So if you follow Wadler gives a reasonable interpretation of comprehension for monads. Now it turns out it's a little bit more complicated than like Wadler does some sleight of hand. If you actually go and carry out a comprehension idea with just a monad in hand, things are a little bit more complicated. So Mike and I actually did that a year and a half ago or so, where we sort of did a generalized Mitchell-Binabu language for monads to try to get some experience and get our hands around what is it to have a notion of comprehension if you just have a monad in hand and not something more set-like. But in general, that intuition is relatively sound, and that's why I went down the path of distributed law, because the Levier theories and their connection to monads is super clear. There's no question about that. But the thing with the thing with collections and monads, it's only a hypothesis, and when you do the distributive law, it will work, but it gets screwed up for notions of negation. So you have to be careful about that as well. So there is this alternate construction that comes out of Christian's approach, but Christian is not currently concerned with the collection logic. So so I can show you what the pathway is, and this is basically going through the Yoneda lemma.
Excuse me, Greg. Are you sharing your screen?
No, I'm going to.
Oh, okay. Just want to make sure.
Yeah. All right. So hang on a second. All right. So the idea is you've got some theory, and you go via Yoneda to a Hom set, and that Hom set is occurring in the category of categories to the theory op. All right, so the morphisms are turned round from there to set. Okay, so you're interpreting sorts you're taking sorts to the functor blank set. So when you fill in a functor, you'll get a functor from the theory op to set, right? And then you go from there via the subfunctors to this the category of posets. So categories are posets are categories. So this is there's sort of a two-level nature to this. And the idea is that we're going to, just get rid of that. That's not useful. What we want to do is we want to generalize this. And the main kind of trickiness in this is, so we want to go from not just to cat, but to V enriched cat. So V is our notion of collection. And here, so we want we want this Hom set, right? So this is their Hom gadget. So this is all the morphisms running from theory op to V, and that itself needs to be a V. And then you can consider taking the subfunctors of that, and so there's two issues: whether poset is the right place to go, and the other. So basically, what we're asking is, where does the collection logic creep in? Is it creeping in here, or is it creeping in here? So that's what we're trying to ferret out in our calculations, is to determine exactly where the collection logic creeps in. Now, what's really important about this this analysis is that there's no explicit syntax mapping for the logic, right? So, and the reason the distributive law was interesting was because we have an explicit syntax for the collection part of the logic. And then the distributive law, you know, lines up nicely because when you combine the theories, you know what you have to, you know, from, there's a kind of language theoretic argument, right? So you're, let's see if I can write this down for you guys. So if you have theory plus some notion of collection, say C, notice that I'm using V above, but let's call it C for collection. That this is really going to be, if these are both monads, then this is really going to, that plus is really going to correspond to, let's see, how do I say this? This really corresponds to all of the different ways you can combine these functors. So if you think of TH and C as letters in an alphabet, right, then it's really going to be TH comma C star. Oops. Meaning, you know, all the different combinations. So TH, so, you know, empty, and then TH and TH squared, and, you know, all of those together with C and C squared, and all of those, and then all the combinations, right? So TH C and C TH, yeah. And in general, it's going to be, you know, TH to the M and C to the N, or C to the M, comma, TH to the N. All right, so that's what that plus as combinations of theories really means. Okay, and
Okay.
Does that make sense?
Can I ask? Yes, yes.
Okay.
Is this somehow similar to this Chinese monoid?
No. The Chinese monoid is just one example of a monoid that has some. The reason I use the Chinese monoid in some examples is the Chinese monoid doesn't just have generators; it also has some relations. So there are some equations, additional equations apart from the identity equations and the associativity equations that hold for the Chinese monoid. And because those equations hold, there's a normal form for every monoid expression. And because there's a normal form, it turns out there's a set of rewrite rules that you can have for the, that will reduce, if you give me a word in the Chinese monoid, so some multiplication, I can run these rewrite rules and get the word down to a reduced normal form. So because there are these rewrite rules, then you can get all three buckets of logic, right? So you get your collection formulae, you get your syntax formulae, and then you get your modal formulae, which have to do with the rewrites.
I see, thanks. And the normal monoid, basically every term is normal form. We don't have any rewrites. Without any additional relations. No, if you have no additional equations, then you just have some multiplication. You don't know how to reduce it further. Okay, thanks.
Right. And so when we're just talking about a normal monoid, since there are no rewrite rules, you only get 2 of the 3 buckets of the formulae.
Yeah,
right?
Yeah. Thanks for clarification. Yeah, now it's completely clear. Yeah.
Okay. All right. So anyway, so when you combine these theories, and what we're trying to do is to show that there's always a path to you want to get a path to C of TH, right? So collections of terms. That's what you're interested in. No matter what, so if these things represent your formulae, right, then your semantics for your formula should be a path from any one of these to here. So if these things are monads, right, then then anything like a t to the m is ultimately via the monad multiplication just going to collapse via flattening down to just a th, right? You just keep iteratively applying flatten. Now you can always flatten these things down. Likewise, if you have a c to the m, you can flatten that down, right? To a c. So monad multiplication allows you to just keep flattening, right? So you just do this generic flattening thing. And that'll get all the stuff in here down to here. And now now if you have C's in front of TH's, you're done. You're golden. You don't need to do anything else, right? Because that's what you're trying to do. But if you have a TH in front of a C, you have a problem. There's nothing you can do without a distributive law. So if you have a distributive law, you go via the distributive law, say D, to C of TH, and voila. Now you've shown that you have exactly the equational things that you need in order to take anything in here to one of those. Oh, and by the way, if you just have THs and you need a C of TH, then you just take the unit, right? And so if you go, this is via the that's via the multiplication, right? And then you go from there to C of TH via the unit, right? Oops. And here, you don't need any THs, right? Because it could be an empty collection. So that's fine. Here is your only bugaboo, right? This one you don't need to go any further. This is just you go by one. You go by the identity, right? Oops. To C of TH. right? And here you would go by the distributive law to C of TH. And so now what this does is it says that in the presence of a distributive law, you can always go from a combination of, terms and collections as formulae to C of TH. So that's a theorem, right? But the problem is that we can't, how do I say this? The notion of collection in computer science and in mainstream mathematics is so broken that building up this syntax and getting that syntax to line up with our notions of collection doesn't work. It just basically doesn't work. So even though the overall structure of this theorem is absolutely true, trying to make this thing line up with our notion of collection it doesn't work for most of our notions of collection. In particular, if this is a notion of list, then we get a no-go theorem for the distributive law. So we're stuck. We can't. So the only kind of collection that we can do are set-like things. So if you restrict it to set-like things, then you run into a problem with the negation. So that's why collections have been really kind of a fly in the ointment. So Christian's construction, which is this top one here, will get you a version of what we're trying to go for, but he doesn't generalize on the collection. He only gets the logical operations from the topos, and that's it. He doesn't get the logical operations to correspond to a wider variety of collections. So what Mike and I are doing is saying, well, where in this thing does the set-like logic show up? Is it here, or is it here, or is it some combination of those two? So what we're looking at right now is we're looking at so the V enriched case, where V is your notion of collection instead of set, and then when you're looking at this generalized Uneda embedding, then this Hom set is also a V, right? And then we take a notion of sub-functor out of there. So that's what we're looking at to make sure that we've kind of exhausted all possibilities. Yeah. So anyway, that's the work. Mike and I are still deep in calculations as to how this works out. So obviously we have a version of this that works when the notion is set, but we'd like a version that works when you have more general collections. That's the basic issue. It's like it's super obvious when you run the naive calculation that the collection part is separate from the term part, which is separate from the modal part. That's really clear. And so we just want to find out where the collection part makes its contribution. In whatever accounts for the construction, we need to find out where the set part makes its contribution, or the collection part makes its contribution, and then be able to generalize that so we can put in a variety of notions of collection. Or if we can find, or if we find out, that there are, constraints. So like, for example, in this case here, what we've discovered is in order to support this at all, V has to at least be symmetrical monoidal closed. So, you know, like you can support, Boolean logic, you can support intuitionistic logic, you can support linear logic. But there are a variety of things that we can't support. You can't support a bare bones notion of list, right? Because list is too impoverished. It isn't symmetric monoidal closed. And that's okay. I'm fine with that, right? All we're saying is that in this setup, the notion of collection has to have at least this much structure to it in order for the notion of collection and the notion of logic to line up. And that's perfectly reasonable. Now,
does that include multi-set?
Yes, it does. Yes. Yeah. So now, just to give you a sense of why I'm fighting so hard for this kind of thing, one of the things that's been a bugaboo for probability for a very long time, or for logic and statistics and those kinds of inferential reasoning, is conditional probability. Bayes' rule doesn't line up well with the notion of logic, right? And there's been a lot of work to try to get that sorted out. But what would be really nice is if we have a framework that generates the logics, right? Then we can talk about, whether and how you can generate a notion of a probabilistic, collection, right? So a notion of distributions, and essentially a notion of implication in that logic of distributions. And that would give you, assuming it's possible, that would give you an account of a conditional probability, right? So that's something that is currently, we don't have a good account of it. And if we can talk about how the collections generate that part of the logic, then we can start to, we have a ghost of a chance of starting to talk about conditional probabilities, right? So that's why, it's these kinds of questions and much larger questions that drive me to want to sort this out at the right level, right? To not be satisfied by a construction that only tells a small portion of the story. So that's what's going on there. I'll also say that I have spent a little extra time in the last couple of days returning to these stochastic rewrite systems, and that is closely related to wanting to have probabilistic versions of these logics, right? So we want fuzzy or distribution-like notions of these logics, and the reason is because the stochastic versions of the pi calculus have had an enormous success in modeling chemical, biochemical, and biological situations. However, one of the things that's really fascinating is that so the initial formulations of stochastic pi fail to meet the bar in a lot of ways. So the equivalence classes that we normally think of with pi, they don't respect the probabilistic interpretations, right? So we know that par together with zero and the processes form a monoid. And those monoid laws are broken in the initial formulations of the stochastic pi calculus. And the notions of bisimulation are they're not pleasant either. They're not treated well either. So that motivated Luca Cardelli and Radu Mardare to revisit a notion of the stochastic pi calculus. Now, there are a lot of desiderata associated with the stochastic pi calculus, their account. In particular, they don't follow Milner's decomposition of the pi calculus in terms of concretions and abstractions. They treat the prefixes as separate, which is very, very problematic, right? Because there's no way to model the information flow, the binding structure that's captured by the input action. So that's really very, very problematic, and at least in my belief, and I think Robin's no longer alive, but I think anyone who is following Robin would say that's very problematic. But at least in their account, they're able to recover the equivalences and show, for example, that the bang can't be recovered. That's appropriate. You would have runaway probabilities if you accounted for bang in terms of the structural equivalence. So that's totally reasonable. Nobody likes the structural equivalence account of bang or replication. The account is an improvement over the initial accounts, but there's a desideratum that has bugged me for quite some time, and that is that apart from the way they treat the binding effect of input, which it's pretty clear that needs to be fixed. That needs a little more attention. The way they address it is they have a probability environment, right? So to each equivalence class of processes, they're assigning an environment which gives you a notion of a rate on a channel. And that's where the stochasticity comes in. So the channels can interact at a variety of rates, and you can write down an integral that uses the rate information to then select which interactions are going to happen. So this would be like in R space, putting a rate on the hash table. Does that make sense? You guys understanding what I'm saying?
I'm not completely sure what do you mean by rate.
So it's the rate, it's the relative rate at which COM events will happen. So you put a rate on a particular channel. So if you have a race condition where you could interact on one channel or another channel, then the rate information is going to tell you which one you to favor.
And this is instead of just using some shuffling to decide, this is like additional rule how we are deciding.
It's additional information. It's not strictly non-determinism now. The rate is impacting the non-deterministic structure.
Okay.
If you're discovering the behavior of a system, using Bayesian methods, you end up with a probability of there being a certain outcome, and you haven't figured out the Markov algorithm or whatever to account for it, but you know that it happens at a certain rate in the system. And the things that happen more frequently are the things that tend to be in control of the system behavior.
Yeah. So, but this doesn't have to be connected to Bayes at all. It's just the user supplies the rate information associated with the channels.
Or the system does.
Right, or the system does. But the point is that the rates are provided a priori. They're input to the execution mechanism. So the issue that I have with their account is that the rates are fixed. These environments are fixed, and there's no way to have action within the system modify the rates. So you can't have any communication event turning around and updating the rate environment. Apart from, you could have channels go out of scope or channels come into scope, but you can't modify that rate map so that a channel that remains in scope suddenly gets a different rate. However, if you recall, I can simulate the rates via the Annihilation Rule. So the Annihilation Rule, if you remember, is one in which we have a for comprehension interacts with an output in the COM rule, not just on the basis of whether the channels are structurally equal as processes, but if the two things annihilate each other, which means is if you take those processes and you run them in par, do they eventually get to zero? And so that's a very recursive rule, right? It allows you to go, you have to prove that it bottoms out, right? And it does bottom out because, zero annihilates zero. So because processes can't be their own, the quote of a given process can't be used as a name in a particular process. You can't, since you don't have the circularities, every time you go down a level in terms of names, you're marching closer and closer to zero. So it's a well-founded notion of execution. And since it's a well-founded notion of execution, you can simulate the different rates by selecting names where there's more annihilation steps. Does that make sense?
Yes, yes.
Right. So basically it takes you longer to run the annihilation. And since it takes you longer to run the annihilation, those that end up stopping sooner go sooner, right? You get those reductions. And so you can simulate rates in this fashion. And because you can simulate rates, you can update the rate thing by updating your channels, right? Whichever channels you utilize, you draw them from a set where the annihilation takes a different amount of time, right? So you basically have available to you all possible rates, and then you can select You can select from those that match. Now that's again, it's still not a perfect match in the sense of what we'd really like is an update to the environment. But this gives you a solution which is closed in the sense that the rate environments they're exogenous to the calculus, right? They're not written. They're treated as extra apparatus, and with this annihilation, it's not exogenous to the calculus. It's apparatus inside the calculus, right? It's endogenous to the calculus. And so that's a step in the right direction. And so I'm just thinking about how to incorporate the rates so that they're on the inside. And this is closely related to, I mean, these considerations are closely related to when my collections are probabilistic. So that's how the two notions are interwoven. So, and it gives you a little insight as to how I approach these problems, right? I'm trying to think about these problems in a holistic fashion, so that so that I nail, so I become aware of all the requirements, and I put enough pressure on the solution that it nails as many of the requirements as possible. Because it's very easy to go down a particular cul-de-sac, right? You know, like saddle points are both local minima and local maxima, right? And so you want to be able to, you don't want to get yourself stuck in a situation where you're looking for a minima, but you don't realize that it's also a maxima. Does that make sense? You guys understand what I'm saying?
Can I ask you about these rates, how you're constructing with annihilation? And is this means that you're choosing different, if we have two receives, and we know that inside one receive is another COM event, and then we will have 0, and in another receives there are two COM events. So this is this is my understanding okay? How you?
Well, just to be clear, let's say we have, for y from at p, right, and then do some stuff, whatever, r, in parallel with at q bang s. Okay, so that's our basic situation. And now just for grins, we could have if we want to really have different rates impacting, then we're going to have to do something like this. We're going to have to do a sum, and then we have for u from at p prime, and we do an r prime. Oh, where is it? Oh, I see. Okay, so there's that. And then okay, and then this needs to be a q prime. Okay, and now let's say So you can see that there's a potential race, right? So just for purposes of discussion, let's say that Q will annihilates P prime, and Q prime annihilates. Q annihilates P, and Q prime annihilates P prime, right? So that's the idea. And now,
so you're not writing this as the same channels. You're saying Q and P annihilates, but they're not the same.
So right, PQ has got to go to 0, right? That's annihilation, and it's not immediately 0; it's eventually 0, right? And P prime, Q prime has got to go to 0 eventually, right? And now what we can say, we can simulate the different rates by making all of these paths shorter than all of these paths. So any path here being shorter than, and you can get like the shortest path by making P and Q both be 0. So this is communicating on at 0, and this is communicating on at 0. And so that's the shortest possible path, right? And if you make P prime be one level up, so it's a 4 that's listening on a 0, and the Q is ascending on a 0, at 0. Then that has to go through one reduction before it gets to 0, right? And so this one goes faster essentially than this one. In other words, it takes less energy to run to ground. And so now you can just to simulate rates, you look at all the paths, right? And you take the average length of the paths, and that's the energy required, right? Right. And whenever, and so you can get relative rates by how much energy is required for one or the other. Does that make sense?
Yes. And when you say shortest or quickest path, you don't think about time. You talk about like com events, or not the time, right? The real time.
And not clock time, com event time.
Okay.
Right? That's the only time that matters, right? Is the evolution of your computational system. There is no other time apart from that time.
Okay. Just want to be sure.
Yeah. No, but to me, that's really important, because I want to argue that time arises from computation rather than the other way around. We don't have the notion of clock is a derived notion. And more generally, space-time is a derived notion that derives from the computation. Right. So that's real, right? So if you're going to follow Wheeler's it from bit program, then what's real is bits. What's real is your notion of computation, and then your physics derives from your notion of computation. So that's so this is within that framework. It's consistent with those intuitions. That's the way to say it.
Can I also ask you on the when you were talking about resource, you said resource is the runtime part. It's not on the compile side, if I remember correctly.
In what context? What are we talking about here?
This R as a resource, and what I want to ask is in this way, what you are showing, execution and the runtime can change the rate and influence which com events will be chosen, or how the computation will continue.
Yes. So this is yeah.
So,
I mean,
I want to ask, can we also apply the same the same way of changing the resource from the computation itself, so that they are not separated completely? Like,
so the thing that you can do with rho is you can do a star, right? So so that's what makes it closed, right? So you can receive a name here, you can and deposit it here. So that's already accounted for in rho. You see what I'm saying?
not completely sure.
Okay. So we have two different capabilities, right? So in particular, let's look at. Let me get rid of this for a second. And get rid of this. Now, suppose that R does this. Star Y. So now S will run. So the resource that was sent is now running. Does that make sense? Right. So rho has always had the capability to change, change what runs, right? That's a basic thing. But you can do more fun things, right? Instead of sending, you can make sense out of this, right? This is not directly in rho, but you can compile it to rho, right? So if I have some other process, say P prime, so I can take P prime par star Y, and then I take the name of that, right? And then I take the name of all of this, and now I send some other thing, say S prime. Okay, so now I've just changed the rate.
Because
right?
we need some.
This allows me to this allows me to dynamically update the rate. So let's compare this process. So let's compare two processes. Okay. We have 2 minutes. Okay. So this process, let's say it sends on Y, it sends S prime. Okay. So this will interact with its environment. So let's go ahead and put an environment in. Okay. So there's some at Q prime, bang, and then let's say, I don't know, T. Okay. So what will happen is this thing, this Q annihilates with the P, right? And then that's going to put S in this position here, right? So we're sending on at S, we're sending S prime. So at S, if it annihilates with the Q prime, then we'll see, oh, sorry, this has to be a 4. Come on. All right. So this thing will be an at S. And if that annihilates with the Q prime, if S annihilates with Q prime, then we'll see T in the mix, right?
Yeah.
Now, if I change this up to that, it could still be that this annihilates with Q prime, but it does so through longer paths. Right? There's additional this P prime. It forces longer paths before you can release T. So I've dynamically updated the rate. Does that make sense?
Yes, yes. See.
And then, so it's 8 o'clock, but then so how this connects up is I can start to control those rates logically. I can give a logical specification through namespaces, right? So I give a logical spec of which rates I want. And that's how it connects up to this stuff here. Right, and this is what I'm going for. I want to be able to talk about. Biological systems with these logics. All right, I need to be able to talk about stochastic versions of these processes, so I can talk about biological systems. So that's why I continue to have these fairly high bar requirements for like we could just stop with Christian stuff and say, okay, done, but that's not the aim, right? I want to be able to talk about a wide variety of phenomena, including these biological phenomena. All right, well, thank you so much, folks. We're late for stand up. I'll see you next week.
Thanks, see you.
Sure.